welcome the next speaker, Mr. Andronov from Odessa National Maritime University on a topic of statistically optimal phenomenological modeling of irregular space signals application to variable stars. So, Mr. Andronov, the floor is yours.
So, thank you very much for allowing to make this presentation. I would like to speak about time series analysis and some applications to variable stars of different types. And so, in fact, the epigraph will be the referee report 25 years ago. And so you see that no sense to make new types and new methods for data analysis. Okay, I will try to show some other methods. Okay, so the zoo of variable stars is very different. You may see here only 8 types of variability, but in fact there are 73 and also a lot of mixes. Of course, making them as a presentation of Fourier transform has no sense, and so we will speak something about this. So in fact, we have good collaboration with different countries, and so the main themes of our collaborations are on magnetic cataclysmic variables, non-magnetic cataclysmic variables, as well as pulsating variables from delta Scuti to long period variables. A lot of new variables have been discovered and also in our team, and so they are mainly or very often they are eclipsing. And of course other stars which are looking here. So in fact these methods have been also used by different colleagues and also by our team for solar variability, AGN, radio sources, asteroids sometimes, and so on. And so, in fact, we work on time series analysis of generally irregularly spaced data. What is a typical situation for astronomical observations? There may be gaps even in satellite observations, but especially when we have surveys from the Earth. And so we try to make complete mathematical models and not to use very oversimplified methods which are very simple, and they are often used because sometimes we may have very large errors if using a simplified method. So periods which differ from true ones by a factor of 2 or a few dozens percent and so on. In fact, I would like to point your attention to some review with many references to original data which was published last year and elsewhere. So you see here above the ADS code for this. Okay, there are many different types, and so for example there are Irregularly type stars with Blaschka effect, and you may see here the curves which differ from night to night, and of course the sinusoid which is here is a bad approximation for this. So in fact there is a modulation. So it's a nice star. Sometimes for long periodic variables we don't have such a clear modulation and periodic modulation of the light curve. Also speaking on variable stars and eclipsing variable stars, I would like to say that we make a phenomenological approximation. Sometimes people want to have physical modulation. We also want to have it, but you may see here that less than 1% of them have additional information, for example, for velocities and then mass ratio, spectral types, and so on. And so the majority, more than 99%, is for such phenomenological approximation. And so, in fact, the problem is not to make a good fitting curve. But you see here a lot of parameters, and sometimes we have to fix some parameters to decrease the space, the number of parameters which are to be determined. Again, looking for the Fourier transform, which should be used as a trigonometrical polynomial, because for randomly spaced data, we don't have regular data, and so simplified formulas for Fourier transform may not be applied. And so we have to find which one is better. So you see here that we have noise, and so an infinite number of harmonics doesn't have sense. So this is one thing. For example, here you have an example of relatively stable light curves, but in fact they differ during this century, and so the period differs. They are at a stadium of a helium flash. And you see that it is possible to make a statistically optimal approximation, not just democratically. We look for a curve, okay, this one is good, or maybe we add something. So we use some criteria for statistically optimal things. Of course, there is a very astonishing approximation which you see here. So, for example, for eclipsing binary stars, it is nice to make a fit for the maximum, but a very bad approximation of the minima. But in fact, there are few thousand stars from a satellite which have been used for this. So we try to make an optimal approximation to do this. And so we have elaborated a new algol variable algorithm which we apply for binary stars. And so the difference is that we have here the reflection effect and also the ellipsoidality effect, but the minimum is maybe computed not from the maximum as in a catalogs, but just from such a continuum. And so it is much better to make some approximations and to fit physical parameters. Okay, I will just show some formula, but it is not so important. So you may see newly discovered variables, and so how good the approximation is. So very different in accuracy, but anyway, you see here algos. But it was interesting to see that not only algos may be done here. And so with our method, it is possible also to determine the depth of the minima for the stars which were believed not to have abrupt beginning and end of this. And so this was the difference, official difference between the algos and the rest of the stars. Okay, so also this method was improved for the case of elliptical orbits and so on. These are intermediate conclusions for this. Everything is written and so on. Also, we tried to find the best approximations for minima. You may see here 14 from around half 100, which we tested for the approximations. Also, we have elaborated a program which is everything in one. So there is a possibility to make fits for the exoplanet transits or eclipsing variables using 21 approximations of 11 times. And so you may see here it is possible to fix some of the approximations or to make automatic choose the best approximation for this. Okay, this is a part of approximations. You may see here that it is not a smooth approximation, but it is based on the near maximum or minimum dates for this. Okay, they have been applied by another student here, and so he found a lot of stars with eclipsing not only eclipses, but also a third body which has an elliptic orbit, and so he has elaborated a program, Python program to use this. So an application to our determination of minima. And he has discovered more than 1,000 stars, new variable stars from the test. And so you may just see, but this is an elaboration, so we don't present results at this conference. Another part of our work is based on cataclysmic variables. You see here different types and also different physical mechanisms which are responsible for variability, which are done here. And so a lot of observations has been done from 1989 in the Crimean Astrophysical Observatory by Nikolai Shakhovskoy, Sergei Kolesnikov, and so you may see here some results. These results were based on CCD observations, and here you see 1 second resolution for the minima. So at upper part, it is 15th magnitude, and here is around 20. And so you see here that very fast increase or decrease, which doesn't correspond to the radius of the white dwarf. You may see here the size of the white dwarf, and you see here the size of this hotspot at the base of the accretion column. Of course, this was made by using fast photometry, 1 second resolution. Okay, there is some scalegram analysis which we also elaborated. In fact, this epigraph that no need for new methods was done for this paper, which was then later published in Astronomy and Astrophysics. And okay, but the epigraph remains. So you may see here some test functions, so signal to noise, and so it is possible to use it to make the best approximation. As well as these horizontal parts, they allow us to here obtain for the noise, which is seen here, and here you may see the amplitude and the period or characteristical period for stars which are not truly periodic. So you may see here that even for the signal to noise 3, it 1/3, signal to noise 1/3, it is more or less okay. 1/10 is bad. And so it is very nice tool for looking for quasi-periodic oscillations. Okay, for long period variables, you may see here a lot of problems, and also with checking bad points and eliminating them. And also you may see some our work on creating the catalog of phase portraits of variable stars, and so you see light curves which are there, and so depending on the smoothed curve, you see either an ellipse for a sinusoidal variation, or you may see loops which are shown here. So some other examples, and also for the stars of RV Tauri type, sometimes people say that there are alternating minima, so deep and weak minimum. And so there are also such curves which are common in physics, but in astronomy they are not so. So other approximations which may be done, they are based on running sign approximation, and so some intermediate situation between the scalegram, the wavelet, and the Fourier analysis. So you may see some stars which show changes from practically constant state to periodic state, which are seen here, and this also is seen for symbiotic stars. The wavelet analysis was also improved for irregularly spaced data. You may see here, and of course there are no results for the gaps. It's obvious. No, okay, so we work with different types of information, our own monitoring in our group and colleagues from abroad, and also use ground-based and space observations. But, okay.
Sorry to interrupt you a minute, but we are sort of running out of time, so maybe a few slides, a minute to wrap up, and a minute for questions.
No, I guess, okay, I will show them very fast, but maybe 2 minutes more, I will ask you for your attention.
Okay, let's wrap in 2 minutes.
Okay, so, okay, we are looking here, and so the situation is that despite there are good CCD observations, they are relatively short, and so we have to use visual observations for decades, and also for you see different things. So again, another sample of a star, and so you see changing shape of these curves which we study, and also a period. You may see here that the period changes very drastically, but a century ago it was 300 days. So this is a star at a helium flash stage, and so we may look for small variations and fine-tuning of this process. Also, some comparison with Bootstrap. You may see that there are outstanding approximations, and so if somebody will be interested to see the details. Also here, a combination of pulsations as well as dimming, like in Betelgeuse or in Air Corona Borealis. You may see here also such approximations, period variations, which are seen here. And so you may see the conclusions for this. So we apply different methods. We have a net of complementary methods instead of one, as they say that Ptolemaios knew the Fourier transform. And so for different types, we apply different methods to obtain this approximation. Now we have some ongoing projects, so of course not so much stars as we have from the surveys. And so I would like to thank you and to show my supervisor who put me into variable stars while I was interested in other things like negative masses, black holes, gravitational lenses, and so on. And so I think that there is some part of work which our group provides in Ukraine. Thank you very much for attention.
Thank you, Ivan. So maybe we have a quick question from audience.
I have several comments, maybe, or question, maybe comments. So we are interested in variations in active galactic nucleus in radio, in optics, and probably your methods can be applicable not only for variable stars, but also for AGNs. Is it right or not really right?
Yes, sure. We may try, but what we will have, we will see. We may see, of course, if we will apply.
So we work together with Artem Sukharev, also from Odessa.
Yes, he is a master under my supervision, but now he has changed this, his supervisor. Yes, I know his work. Yes.
In this question, probably not so actual because we already know your methods in this case, so we use them.
I think regions. Not so, because it was a quarter of a century ago. So now there are many new methods which we have elaborated.
Yeah. Thanks for joining us.